Okay, so hi, I'm Mario Malinconico, Product Manager and Senior Radiochemist in Comecer. The title of my presentation is Fully Automated Commercial Cassette-Based Production of High Purity Copper Chloride from Solid Nickel-64 Target. This study is in collaboration with this study is in collaboration with SAMRI, South Australian Health and Medical Research Institute in Adelaide, and in particular the Unit of Molecular Imaging and Therapy Research, MITRU, and also the University of Adelaide. So for the solid target, we use the Dalceo system. Dalceo system has different configuration. Dalceo metal for the production of different isotope and also copper 64, the one we produce in this study, and Dalceo halogen for the production of iodine. Dalceo is made of different modules. The first two are the PTS and cooling system. The PTS is the real target connected to the cyclotron. For this study, so in MITRU, we have a GE cyclotron connected to a beam line, which is connected to the PTS. The PTS automatically will transfer the shuttle from the radiopharmacy to the cyclotron and automatically will put in position the shuttle to the beam port, basically, and getting ready for the irradiation. Working together to the PTS, there is the cooling system to cool down the temperature during the bombardment with water and helium. In particular, the water is going to cool down the back part of the shuttle, and the helium is going to cool down the upper part of the shuttle, where actually we really have the material to irradiate, in this case, the nickel-64. Also, about the shuttle, the one we use in this study is the plating shuttle made of aluminum, so it's a body of aluminum with inside platinum. Inside there is platinum, and on the platinum we are going to electroplate the material. It can be used also for the gallium chemistry. There are also different shuttles for different isotopes to be produced with the Dalceo system, but in this case we focused on copper 64. The other module of the Dalceo system is the EDS. The EDS automatically transfers the shuttle from the radiopharmacy, because the EDS is inside, of course, anode cell, to the PTS. Also, it called back the shuttle after the irradiation, and it placed the shuttle after the radiation to the dissolution position. It's also possible to perform in the EDS the electroplating of the material, the rich material. So here there is an electroplating circuit made of a pump, two valves, and an electrolytic cell. Inside the electrolytic cell we have the anode, which is platinum, and the cathode basically is the platinum inside the shuttle. We apply a voltage and we start to electroplate the material. Connected to the EDS, there is the chemistry module, which is the Taddeo PRF. The Taddeo is a disposable cassette module. There are two syringes. There are also some position for the technical gas, reactors, and so on. It's possible to use a commercial production kit. In this case, we use the copper 64 production kit. And basically what the Taddeo does is taking with the syringes the acid, pushing the acid through the EDS, start the dissolution. After the material is dissolved, the purification will start. So the aim of the study is focusing on obtaining high purity copper chloride via cassette-based automated separation method using a one-column approach implemented on the Taddeo PRF chemistry platform. For this study, we use two different purification cartridges, the TK201 from Triscam and the AG1X8 from Bioride. Also, one of the aim is increasing the yields and the quality of the final product. So let's start. Nickel 64 powder has been used to prepare nickel chloride solution. Nickel chloride has been electroplated on the shuttle. The electroplating process takes from 4 to 8 hours. At the end of the electroplating, the plating looks like this. So it has a diameter of 8 milliliters. We have to clean the shuttle because otherwise it can be dirty of the solution, and we don't want to bombard different material except nickel 64. So cleaning with the water, ethanol, and then dried with technical gas. Then the shuttle has been transferred to the PTS, from the EDS to the PTS, and the bombardment, the proton bombardment is started. So the nuclear reaction is nickel 64, proton, neutron, copper 64 at 14.5 MeV. At the end of the bombardment, the EDS called back the shuttle, and the purification, the dissolution and purification with the Tadeo PRF will start. At the end of the process, we will have copper chloride in hydrochloric acid. The timing is different because in this study we used two different resins, and let's see the results. So this is what it looks like, all the process on the software. So again, the syringes will take hydrochloric acid, pushing the hydrochloric acid through the shuttle, and then pushing everything to the cartridges. This cartridge is different, or Triscam 1 or Bioride 1. For the Bioride 1, the target, the irradiated target, has been dissolved with hydrochloric acid 6 molar. Every time we use 1 milliliter of this hydrochloric acid, and for the first and the second dissolution, we heat it up the temperature at 90 degrees. Then all the dissolved material will be pushed through the column, and the purification will start. Hydrochloric acid 6 molar, in particular 40 milliliter, to remove all the nickel 64 and collect it again, because we can use it for the next time. 20 milliliter of hydrochloric acid 2 molar to collect the cobalt made from the proton alpha nuclear reaction, so it's cobalt 61. And finally, hydrochloric acid 0.5 molar, 8 milliliters, to the final product. All the process take 180 minutes. At the end of this process, we have to evaporate till dryness the copper chloride, and then redissolve to give 0.05 molar hydrochloric acid solution with the radioactive concentration of 15 gigabecquerel per milliliter, or the end user specification. About the Triscam resin, so TK201, the situation is a little bit different. The dissolution of the target is almost the same, but we use hydrochloric acid 5 molar. The purification is faster. So only hydrochloric acid 5 molar, at beginning 9.5 milliliter, then additional 4 milliliter to remove the nickel, but in this case we also collect some cobalt. And finally, hydrochloric acid 0.05 molar to get the copper chloride. All the process take only 90 minutes, so half the time. And as always, the final product will be completely evaporated at 120 degrees Celsius, and then reconstitute again at, with the hydrochloric acid 0.05 molar to get a radioactive concentration of 15 gigabecquerel per milliliter, or the end user specification. So results. About the irradiation yield, we can see that if we compare the Bioride 1 with the Triscam 1, we don't have huge differences. We can recover a little bit more copper from the Triscam resin, so almost 88%, comparing the Biorad resin where we actually recover only 72%. An average of copper activity per hour is 5.64 gigabecquerel per hour with the Triscam resin and 4.45 gigabecquerel per hour with the Biorad one. But huge difference is the quality of the final product. So with the ICP-MS analysis, we've seen that we really decrease a lot the nickel with the Triscam resin. So from almost 20,000 to almost 6,000 parts per billion. And also the copper is almost the same. The iron, the aluminum, and the zinc is much better with the Triscam resin instead of the Biorad one. So, conclusion, the key finding of this study was the adoption of the TK201 resin, so the Triscam one. Using an optimized purification protocol, we were able to decrease metallic impurities. We had developed a fully automated production of copper 64 using commercial and widely accessible equipment, consumable, and reagents. So I really want to thank a lot William, Curtin, and Hugh. William from the University of Adelaide, and Curtin and Hugh from Metro, so summary, still in Adelaide. All the data were collected in Metro, and I thank all, and I thank you all for the opportunity, and thank you.